So we're going to continue our kind of basic development of graph theory now with the introduction of a very important class of graphs, the bipartite graphs. So let me start with the main definitions here. So a bipartition of a graph G. So I'm defining the concept bipartition. This is going to be a pair of disjoint subsets of the vertices A and B, whose union is everything. So A and B are both subsets of the vertex set of G. They're going to be disjoint, and their union is going to be everything, all the vertices. So A intersect B is empty. A union B is the whole vertex set. But the key condition, I mean, so far I'm just describing a way of splitting the vertices in two. The key property here, in order to be a bipartition, is that every edge of the graph has to have one end in A and one end in B. So your bipartition is going to be a pair of subsets A, B, A comma B. They're disjoint and their union is everything. So this is just there's just some way of splitting the vertices into a set on the left and a set on the right. That's all we're describing. So a partition, okay, it's not quite a partition because a partition can't have the empty set. So you're allowed to split and you're allowed to have A or B be empty. But all you're doing is you're splitting the vertices into two sets, a set on the left, a set on the right. Every vertex is either on the left or on the right, but not both. And the special rule here, in order to be a bipartition, is that every edge has to go left to right. So the satisfying the rule that every edge has an end in A and an end in B. So and if your graph G, and so not every graph has a bipartition, but if your graph G does have a bipartition, then we call it bipartite. So let me just draw a bipartite graph. So if I wanted to make a bipartite graph, I'm going to have two sets, A and B vertices. You don't have to put boxes around them, but you're welcome to do so if you like. So some vertices will be in A, some vertices will be in B. But the rule now is that every edge has to have one end in A and one end in B. So every edge is sort of going between the two sets A and B. So you're forbidden from having an edge with both ends in A or both ends in B. And in particular, by these definitions, we know that a bipartite graph cannot have a loop, right? You're not allowed to have a loop edge because every edge has to have an end in A and an end in B, and that's not going to happen. That's not going to be satisfied by a loop. So a bipartite graph can have parallel edges. That's perfectly allowed. You can have two edges in parallel between A and B, but you're not going to be allowed to have loops. Okay, so let me just draw a bipartite graph here. Sure, why don't I? So here I'm drawing some bipartite graph with bipartition AB. We also have a complete bipartite graph. I'll just define it on the same page. I think I have enough room. This is simple enough. So the complete bipartite graph is going to be a simple graph that's bipartite, and so it's going to have m vertices on the left and m vertices on the left and n vertices on the right, and you're just going to have all possible edges in between those, all the edges in between those two sets. So I'm declaring that this graph is going to be bipartite. So you're not allowed to have edges between the vertices on the left and not allowed to have edges between the vertices on the right, but you'll have all possible edges between left and right. Of course, I've said the graph is simple, so there's no parallel edges here. Just for every vertex on the left and every vertex on the right, there will be one edge between them. So Km comma n, this is the complete bipartite graph. Actually, let me say A here. So this is a complete bipartite graph. It's got bipartition AB. Where you're going to have m vertices on the left, n vertices on the right, and every vertex in A adjacent to every vertex in B. Okay, so we've seen a bunch of different graph families. I'm just introducing yet another one here. So we have the complete graphs, right? We know what K1 and K2 and K3 and K4 and so on are, right? The graph K sub n is a simple graph on n vertices where every pair of vertices is adjacent. The complete bipartite graph, now it's going to come with two parameters, m and n, and it means that you're making a bipartite graph with m vertices on the left and n vertices on the right. So you're making a bipartite graph with m vertices on the left and n on the right, and you're going to have all possible adjacencies subject to that bipartite restriction. So you're going to have all possible edges between A and B. Okay, let me cut out this drawing and give an example of a complete bipartite graph. So for instance, so these are now coming with two parameters, right? But for instance, K14, that would be this guy. K23, you'd have two vertices on the left and three vertices on the right. And all possible edges in between. So maybe just for clarity here, I'll circle the sets A and B. But you certainly don't have to do that when you draw this in general, right? It's just a graph. But when we say it's a bipartite graph, that means it has a bipartition, and that bipartition is giving you a set of vertices on the left and a set of vertices on the right. Let me just take a moment to point out that you are permitted to have a bipartition where one of those two sets is empty. So you are perfectly allowed to have a bipartite graph where the set on the left is empty. It's not going to be a very exciting graph, right? If you make a bipartite graph where the set on the left is empty, then you can't possibly have any edges in your graph because all of those vertices on the right can't be adjacent to one another.